Alright, welcome to our lesson on the limit of a function. So this concept of limit is really it's fundamental to calculus, to our development of calculus. So I've just written down kind of the formal definition. So your formal definition, well, it's not that formal, but it's our definition. So the limit of a function f at x equals a means the function approaches the number L as x approaches a. So we're going to see, well, let's look at an example to kind of see what that means. So let's say we're looking at the function, let's take a simple one like f at x equals x squared, and we'll take a, so this number, well, that's not right, a, that's right. We want to figure out the limit, so limit, let's read it like that, as x goes to 2. So we want to see what this function approaches as x approaches 2. So one way you could do that is to just do a table. So x, and here's f at x. So we're saying x is approaching 2. Notice it doesn't equal 2, but it gets close to 2. So pick numbers close to 2. Let's say, I don't know, 1.9. That's a number close to 2, right? So if x is 1.9, then what would f at x equal? So it's 1.9 squared. So you'd get 3.61. Ooh, why'd that come out so dark? And now, okay, so 3.61. But we want to get as close to 2 as we can. Well, as possible. So we can actually get closer than 1.9, right? 1.99 is a little bit closer. So if x is 1.99, then this would be 3.96. We can even do better. 1.999, even closer. And f at x would be 3.996. And then, you know, you can keep going, more and more nines, closer and closer. What you might start to see, you probably see that this is getting closer and closer to the number 4. As long as we don't let x go all the way to 2, then this is never going to quite be 4, but it's going to get close to 4. And actually, you could take numbers above 2, right? So we in this case, we approach 2 from below, but you could take a number like 2.1, 2.01, 2.001, and then see what's happening to f at x. So 2.1, you would get, I think you get 4.41. And then I'll let you guys do the rest, but you're going to notice this is also going to approach 4. So it looks like the limit as x goes to 2 is approaching 4. And the way we're going to write that is like this. Limit as x goes to 2 of f at x is equal to 4. So limit. And another way to see this is by doing a graph of, oh, nice graph. So that should be vertical, obviously. A graph of x squared, so you know x squared looks like that. Here's our x, or y. Here's f at x equals x squared. So when x is 2, f at x would be 4. So what we're thinking about is as we, approach 2 from this direction and this direction, what number are we approaching? Well, we're approaching the number 4. So in our definition, that's the L. L is equal to 4. So that's what we mean by limit. Now, one question you're probably asking right now is, why are we doing limits? Couldn't I have just evaluated the function at 2, right? If I put 2 into this function, I get 4. Why do I need this concept of limit? And in this case, you make a good point. In this case, sort of the limit is equal to what the function is equal to, but that's not always going to be the case. So sort of the more interesting example would probably be when that doesn't happen. So let's do the limit as x goes to 1 of, let's take something like x x squared minus 1 over x minus 1. So this is your f. Notice the domain of f is the set of all x real numbers such that x does not equal 1. So we're evaluating the limit at a number that's not in the domain. So you couldn't do what we did in that, what you wanted to do in that last example, where you just sub the value into the function, because the function is not actually defined at that function. So, at this point, our only real way to do this is to do a table. So, same way we did it before. So you take a number like 0.9, 0.99, 0.999, and if you put that into f, what you're going to notice is this one's 1.9, 1.99. You can confirm this with your calculator if you want. And then sort of that pattern continues, and you might say, okay, that looks like it's going to 2. And let's try numbers of x above 1 this time. So closer to 1, but this time above. So 1.1, 1.01, 1.001, and then you're going to get 2.1, 2.01, 2.001. So again, looks like it's approaching 2. So therefore, it appears that the limit as x goes to 1 of this thing, x squared minus 1 over x minus 1, is equal to 2. And in this case, you couldn't just evaluate this at 1 because the function doesn't exist at 1. So again, you could do this at a graph. Actually, this function here, f of x equals x, if you did want to graph it, you can simplify it by factoring the top. And then notice there's a common factor on the top and the bottom. So f of x is actually equal to x plus 1 as long as x does not equal 1. So what's happening at that 1? Well, you might remember that means there's a hole. And what we just figured out is where that hole is. So this is 1, 2, 3. So f of x is going to look like the line x plus 1. So that's a linear line, y-intercept of 1 with a slope of 1. Wow, I guess I could -1. This would be number 2. But there's a hole right here, an open hole. So that's y. And this is the line f of x equals x squared minus 1 over x plus 1. Oh, sorry, minus 1. Okay, so that's what we just figured out. We figured out where that hole is. So notice, even though the function doesn't exist there, as you go along the function from the left and the right, it's still approaching a number. It's still approaching this number 2 at 1. Okay. So that's how, hopefully this example, does a little bit to show you that even though a function, what a function is equal to at the value does not necessarily correspond to what the limit is, because the function might not exist, but the limit might.